All right, so we'll go ahead and get started with part 2 of this video. I'm putting the notes in the same note thing as last time, just so you don't have to download 2 sets of notes if you download this file later. The video will be in 2 parts though. So let's go ahead and see where we were, what we need to do. So what we just did in the previous video was we did an example of the midpoint rule. Now we are going to come back and do another example of the midpoint rule, at least we probably are, but we need to talk about the other 2 methods, the Trapezoidal Rule and Simpson's rule first. So let's get those out of the way. So we'll do Trapezoidal Rule first. Trapezoidal Rule. All right, so we'll do a little tiny bit of derivation here to give you an idea of what's going on. So first of all, a trapezoid looks like this. So trapezoid is like a rectangle, but the top is not going to be flat generally. So this is going to be a trapezoid, okay? And the area of a trapezoid is going to depend on the measurements, of course. Now the area of a rectangle is like the width times the height. So we're still going to have a width, and we're still going to call it delta x. That's the same as the midpoint rule and all the rules. Now the heights are still going to be y values. So let me just call this one y0 and this one y1 for the heights on the left and the right side of the trapezoid. Well, it turns out that the way you get the area of a trapezoid is going to be not the width times the height, but it's the width times the average of the heights. So if you have height y0 on the left and height y1 on the right, the average of the heights is y0 plus y1 over 2. Okay, and that's it. That's the average, that's the area of a trapezoid. And something you can do is you can take this 2 here, you can take that 2, and you can just move it over with the delta x, and you could write the formula this way. You could write the formula as delta x over 2 parentheses y0 plus y1. That's another way to write it. Okay, now what I want to show you is what is the area of a bunch of trapezoids. So the area of a bunch of trapezoids. Okay, so let's just imagine a scenario where we've got, what I'm going to do is I'm going to draw all these in, and then afterwards I'll write on them. Okay, so I just drew a bunch of vertical segments. Now I'm going to connect them with lines. And there we go. So I've got a bunch of trapezoids now. I don't know why I'm putting dots there. That doesn't matter at all. So there's a bunch of trapezoids, right? A bunch of trapezoids. So if I label the sides the way that I did in my picture of that one trapezoid, maybe this first height is y0, and the next one is y1, and the next one is y2, y3, y4, y5, y6, and y7. Okay, now let's say all of the widths are the same. So let's say delta x, delta x, delta x. I'll have to write them all. I don't need to say them all out loud. Delta x. Okay, so there's a bunch of trapezoids. Now, if you want to get the area of that, you have to add up a bunch of areas like this one over here. And that's fine, we can do that, and we are going to do that. So the area, right, is going to be the area of the first trapezoid. Now the area of the first trapezoid, I know I can write it this way. So the area of the first trapezoid is delta x over 2 y0 plus y1. Right? Now the area of the second trapezoid, this one, you're going to do the same exact thing, but it's not going to be y0 and y1. It's going to be delta x over 2 y1 plus y2, right? Its sides are y1 and y2. For the third trapezoid, right, this one, it's delta x over 2 y2 plus y3, right? And so on. And I'm already tired, but I'm just going to put a dot, 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 and I'm going to write the last two. Delta x over 2, the second to the last one, this one, would be y5 and y6. I don't know why I wrote it like I was writing a fraction. y5 plus y6. And then the last one, which I did not have room for, was delta x over 2 y6 plus y7. Okay, so that's all of them that I drew. And I just put a dot, dot, dot in the middle. But if you look at what happens here, something interesting will happen if I take this and I factor out the delta x over 2. Because what I'm going to get is here, y0 plus y1, and then here, y1 plus y2, y2 plus y3, y3 plus y4, y4 plus y5, y5 plus y6, y6 plus y7, right? So you end up with all that stuff. But take a look though. You've got a y1 and a y1, y2 and y2, y3 and y3, y4 and y4. I'm just gonna cheat here. Not cheat, but just highlight them here. Oops, that last one I should not have drawn. There, right? So each pair that I highlighted are the same y values. So you get delta x over 2, and you get y0, 2y1, 2y2, 2y3, 2y4, 2y5, 2y6, y7. All right, and so what I want you to notice about this is you have a y0 and a y7, right? And the first one, right, there's a 1 coefficient there, just coefficient. And then on the last one, there's a 1 coefficient. But then all the middle ones have a 2. All have coefficient 2. All right? And that's what happens because of the fact that each y value is actually each y value is the height on 2 different trapezoids, and so you end up they end up with a coefficient of 2 when you multiply it out. So that's what happens. Now let's think about that in terms of an integral now. So for an integral, integral a to b y equals, or not y equals, integral a to b f of x dx, right? We've got, if you have an a and you have a b, right? And you're going to try to use trapezoids to represent the area, what you're going to do is, let's see, 1, 2, 3, 4, 5, 6. Of course, it's not evenly spaced. I'm going to move that B. That was supposed to be red. Okay. So if you put B there, okay. If you do these trapezoids where you get these heights here, like that, and then for the top of the trapezoids you connect those with a straight line, stop making that level. It just wants to snap. So I can't get those. It's supposed to go from dot to dot, but it really doesn't want to go dot to dot. It wants to go snap to a different value. So that's really annoying that I can't draw it. Okay, it's close enough. Okay, so just imagine it goes dot to dot. The point is that the tops, they're not exactly equal to the red curve because they're straight line segments, okay? So there you go. And if you had, you know, if you added up the area of each of these trapezoids, then you're going to get a formula that's just like the formula that we had up here. Okay, so for an integral like this, you'd be able to say that the integral is going to be approximately equal to, so I'm going to say the integral of f of x dx is approximately equal to, we're going to call it Tn. That's the trapezoidal rule approximation. Use a T for trapezoidal, where Tn is going to be delta x over 2, and then y0, 2y1, 2y2, dot dot dot, 2y y in minus 1, and then y in. Okay, and you're getting those from the y values here. Right? Does that make sense? And then the delta x is still the spacing on the x-axis. So that's the formula you would get. Now, that's not enough to calculate it there, right? I mean, it is and it isn't, because you have to calculate like what's the delta x, what's the y0, you know, like all that stuff. So this is going to be for delta x is going to be b minus a over n. That's the same as it was for the midpoint rule. And then your x's are going to be done this way. So x0 is going to be a. Now, this is a little bit different. So you're not going to remember, or maybe you'll remember this from the last lecture, but when we defined the x values for midpoint rule, we started with a 1, and the first one was a plus delta x over 2. And that was to get it to the midpoint because it was the midpoint rule. We don't have any midpoints when we're doing trapezoidal rule. So actually your first x value, we end up calling it x or x0, and it's just a. And then the next one is a plus delta x, and the next one is x1 plus delta x, and then the next one is x2 plus delta x. You keep going until you get to xn, and xn is going to be, you know, x in minus 1 plus delta x, but also it's going to be b, right? Because you start at a and you end at b. So your x values start at a and end at b. So you have those. There's an alternate formula, by the way. So an alternate formula for these, if you want to calculate it from a, is a plus 2 delta x would be x2. x3 would be a plus 3 delta x, and so on. And if you want to add that here to the last one, you could say xn is a plus n delta x, but it's still b. Okay, so these are the x values. Really? Really? All right. Right, you have your x values. You're going to have your y values. Your y values are just going to be y equals y0 is f of x0, y1 is f of x1, etc. and until you get to yn is f of xn. Okay, so you've got x values, y values, delta x, and the formula. So that's everything you need in order to calculate the trapezoidal rule for a problem. So I'm going to get a problem, and we'll do it with the trapezoidal rule instead of the midpoint rule. All right, let's try it. Use trapezoidal rule with n equals 4 subintervals. Change to the eraser on me. Subintervals to estimate integral from 2 to 6 x squared plus 7 dx. All right, so the steps are very, very similar to the midpoint rule. It's actually even easier to calculate it though. So trapezoidal rule will be easier. So, not part A, step 1. So step 1, you need to calculate your delta x. So delta x, like always, is b minus a over n. So for us, delta x is the b and the a. Remember, they come from your problem. So the b is 6, the a is 2, that's the limits of integration, and the n is the number of subdivisions, is 4. Now, it doesn't always come up even like this, but 4 over 4 is 1. That's a nice delta x. Makes it really easy. But often it's not 1, so don't count on that. That's not something that always happens. All right. Once you have the delta x, you need to calculate your x's. It's really easy. You could even, if you want to save space, like you can calculate it this way. Right? Like x0 is a, x1 is a plus delta x, x2 is x1 plus delta x, right? Up to xn, I'll say n, xn minus 1 plus delta x. If you're trying to save space, then maybe you don't want to go vertically there. Maybe you want to put it in a table that's horizontal, and you can save space. You could have done that for the other problem as well, but I didn't. I don't even know why I did that. Oh yeah, I do. All right. Erase that. All right. So what do we have? We're going to calculate an x0, an x1, an x2, an x3, and an x4. And I know I stop at 4 because n is 4, right? So stop there. And then I also know that this is supposed to be a, and I know that if we're doing it right, we should end at b. So what's a? A is 2. And then all you do from one to the next is you just add delta x, which is 1. So we're just going 2, 3, add another delta x, 4, add another delta x, 5, add another delta x, 6, and that's actually b, and we're done. So that's it for the x values, okay? Very easy. It's harder when there's fractions, but it's still not that hard. So you just add delta x to go from one to the next one. Step 3, you need to calculate your y's. Again, you could do it with like y0 is f of x0, y1 is f of x1 until you get to the end. If you'd like to, you could put that in a horizontal table and it'll take up less space. So you can go like f, I mean, you can, but like xi, yi. You know what? I don't even like that. That's not going to be good because you're not going to be able to see it next to it. So I'm erasing that. I want to see the values, or I want to see more than that would show in the table. So like y0 is f of x0, right? But x0 we have from our problem is 2. So we need f of 2. Now I didn't write f. What's f? Right? We need to know that. So from the integral, stop. Why would you do that? Stop. F of x was the integral that we were integrating, which is somewhere x squared plus 7. Right? Seriously? X squared plus 7. So that's what we're integrating. So y0 is f of x0, which is f of 2. So that's 2 squared plus 7. And y1 is f of x1, which is 3. So that's 3 squared plus 7. y2 is f of x3, which is 4. So 4 squared plus 7. y3 is f of x3. I don't know why I wrote it this one, which is f of 5. 5 squared plus 7. And y4, which will be done, is f of x4, which is f of 6, which is 6 squared plus 7. I don't know why I wrote like this extra thing in just for the y3 and y4, but you could write them for all of them or none of them. All right, so you grab a calculator and you have to calculate these. So like 4 plus 7 is 11. 9 plus 7 is 16. 16 plus 7, 23. 25 plus 7, 32. 36 plus 7, 43. All right, so we got all our y values. So we have all of our y's right here, nicely calculated. All right, once you have that, then we can actually calculate the trapezoidal rule approximation. Right, so we're using this formula, delta x over 2, and y0, 2y1, 2y2, dot dot dot, 2y in minus 1, and then y in. Now for us, right, we're doing y4, so t4 for 4 is delta x over 2, and it's just going to be y0, 2y1, 2y2, 2y3, and when you get to the last one, it's 1, y4. So for us, this is what we're going to be using. So we just put in the numbers. So we need delta x. What's delta x? You have to find it, calculate it. Well, we already calculated it. It's 1. 2 is 2. And then here we just put in the numbers. So we just have 11 plus 2 times 16 plus 2 times 23 plus 2 times 32 plus 43. That's it. So you work this out on a calculator. 11 plus 2 times 16 plus 2 times 23 plus 2 times 32 plus 2 times, no, just plus 43. I get 182. So it's just 182 times a half. So it's 91. Right, so that integral is 91. Well, the integral is not 91. What we're saying is this. So the integral that we were given, which is 2 to 6 x squared plus 7 dx, is approximately equal to t4. That's the trapezoidal rule approximation with 4 subdivisions. and that is 91. Okay, so the answer to the question is 91. Oh, right, okay. Let's do like a part B. I'm gonna make it up. B. There was no part B, now there is. Part B is find the absolute error. Let's just do one of those. Hold on a second. I have 91, but that's not supposed to be the right answer. Let me just double check this. Huh. Yeah, I added it wrong. This is 196. And what's really weird is I'm looking at the line above it, and like I can't see what I typed in different on the one that came up 182. Oh yeah, I can. Okay. Yeah, I just typed it in wrong. All right, so it's 196 over 2, which is actually 98. Okay. 98. All right, so find the absolute error of the approximation. All right, so remember how to do this. You need to know the approximation and the real thing. So, right, the approximation is 98. The true value is the actual integral from 2 to 6 of x squared plus 7 dx. Now, again, you can definitely do that integral by hand. We did the last one by hand. It was like the same integral. But, you know, it's not cheating on these to make a computer do it. So if you want to go like integrate x squared plus 7 from 2 to 6, enter, and just get an answer, and so it's 292 over 3, that's fine. 292 over 3. Where are we? Okay. Are you kidding me? It just, okay, sure. Awesome. All right. So, number one, what was it? We said the approximation. So the approximation was what we got on the previous one, which was 98. Fix it again. 98. 98. Okay. So the approximation is 98. The real thing, true value, is the integral from 2 to 6 of x squared plus 7 dx, which is 292 over 3, just from the computer, right? You can easily do that by hand. Then the error, absolute error, is simply the, well, in absolute value, is the absolute value of the true value minus the approximation. So you just put in the numbers, and we're just seeing how far off we are. So the true value is 292 over 3, and then minus 98. And you just do that and absolute value it, and you get what you get. So I do that on a computer, or I mean, I'm using a calculator that can do fractions. 292 over 3 minus 98 is going to be 2/3. And there you are. So what that's saying is that's how far off we were, right? Because 292 over 3 is 97.3. So this is 97.33, right? So that's the real answer. And then this is the answer we came up with, was 98. How far off were we? 2/3. Okay, so that's absolute error. And that's the trapezoidal rule, right? So all you really need is, the formula for trapezoidal rule here, and you need to know how to get the delta x, the x's, and the y's. All right. Let us look at Simpson's rule. Now, Simpson's rule, I'm going to warn you, I am not going to derive it in as much detail as we did for the trapezoidal rule. Okay, so I'm not really going to derive it at all. All right. So just think about this. On the midpoint rule, okay, I'm going to use big rectangles because I'm lazy. So bad. Okay, so when you do the midpoint rule, right? Midpoint rule. I'm just giving you the idea. The midpoint rule, you can think of it this way. You're approximating the function, so the curve, approximate the curve as piecewise constant. Constant just means level, right? Piecewise constant. And then to get our approximation of the integral, we're counting up the exact area under those piecewise constant curves. So approximate the curve by constants, and then we are, pick the color, stupid, exactly finding the area under those constants. Okay, find area under the curve, the approximate curve. All right, and that's the midpoint rule. Now the trapezoidal rule, if we draw that, okay, remember how this worked was you were, oh, my curve is too straight here, but you were approximating your function with trapezoids, right? So we know that, but if you think about it, what we were doing was we were approximate the function, so not the integral yet, approximate the curve as piecewise linear, right? So instead of being constant, right, level, they're lines, but they're slanted lines. So approximate the curve by piecewise linear, and then we were finding the area under the curve, under those curves. And that does a better job, right? So the trapezoidal rule does a better job of following the function. So what Simpson's rule does is this. So Simpson's rule, I guess I can put it here. Oh, come on. So what Simpson's rule does is actually more complicated. So what Simpson's rule does is it actually approximates your function with quadratic curves, piecewise quadratic. Approximate the curve as piecewise quadratic. That means it can have curvature now. So what's going to happen is if you have a function that has a lot of curvature to it, which I didn't draw one that did, unfortunately, but if you did, then when you're approximating the curve as piecewise quadratic, it's actually going to have some curvature there, and it's actually going to have some curvature there and there and there. And so the top is actually going to be curved in Simpson's rule. So when you have little gaps here, right, like there's a little gap where the curve and the straight line don't match, well, you're still going to have that kind of thing happening here in Simpson's rule, but the way it doesn't match is going to be like your real curve might be like this might be f of x. Well, I shouldn't do that. Hold on, I should use the same colors. Like your real curve might be like this, for example. And then your approximation for the curve might be like this. Really, come on, just let me draw a curved line. And they still don't match exactly, right? They still don't match exactly, but at least there's some curvature, and the fact that there's some curvature means that it does a better job of approximating the function. So when you approximate the curve as piecewise piecewise quadratic, and then you compute the area under the curves, this is generally going to do a better job. So this is generally the best out of these three. Okay. Yeah, so it's generally the best out of these three methods because it's approximating the function with a more complicated type of thing. And yeah. Now, what is it? Well, I'm not going to do any more derivation than what I've already done. I'm not going to like derive the formula of the quadratics and that kind of thing. It's too much trouble, so we're not. But what I will do is just describe it, right? So the steps are going to be as follows. Step 1, you're going to compute delta x, which is same as before, b minus a over n. You're going to compute the x's, same as the trapezoidal rule. So like x0 is a, x1 is a plus delta x, x2 is x1 plus delta x, dot dot dot, until you get to xn, which is going to be a couple things, xn minus 1 plus delta x, or actually it's also equal to b. All right. Then you compute your y's. That's the same as the trapezoidal rule. And then you can compute the actual Simpson's rule. All right. Now Simpson's rule is going to be this. So I'm going to say S in for Simpson's rule, and it's a different formula. So it's delta x over 3 instead of delta x over 2 for trapezoidal rule. And then the formula is y0, 4y1, 2y2, 4y3, dot dot dot. You keep alternating 4 and 2. 2yn minus 2, 4yn minus 1, and then yn. All right. let's describe what we're looking at here. So first of all, the one at the beginning and the one at the end have ones, right? One, no, that's not what I wanted. One coefficient. Or I should say coefficient 1. Coefficient 1. All right. Now in between, it goes 4, 2, 4, 2, 4, 2. Coefficients alternate 4, 2, 4, 2, 4, dot, dot, dot. But has to end with a 4. Oops. Starts and ends with a 4. Okay, so in the formula for Simpson's rule, that's how it goes. So 1, 4, 2, 4, 2, 4, 2, 4, 2, however far you go, and then it ends with a 4, and then the 1. Right, so 4, 4, 4. I don't know why I highlighted that, not instructive. Okay, so that's the way it goes. And the way you make it happen, by the way, the reason you can say that it starts with a 4 and ends with a 4 when you're alternating is because of this, and this is very important. N must be even to do Simpson's rule. Okay, so you got to know that. And in being even is what makes it so that happens, that the fact that it starts and ends at a 4 when you alternate. All right, so that's Simpson's rule. And of course we need to calculate one, so let us do that. Cheat, submit. That's midpoint rule, cheat, submit. Midpoint rule, cheat, submit. Sorry. I mean, I don't know why I'm doing this. It doesn't matter if I write one or not. Okay, I give up. Let's do it. Let's do this one. So use Simpson's rule. With n equals, I'm going to go 6. This is going to be longer than the others just because I'm making it longer on purpose. To compute, or to estimate, I should say. And we're not going to do any error stuff here. We're just going to estimate the integral from 0 to 3 of 6x squared plus 3x dx. All right, so this is a perfectly okay problem, just very straightforward Simpson's rule. And we're just gonna go through it. So step 1. Find delta x. Delta x is b minus a over n. So 3 minus 0 over 6. So it is 1/2. Step 2. Calculate your x's. All right. Now, your first x, we number them at 0. So something you may not have noticed, but we did, was midpoint rule, we started numbering at 1. And for Simpson's rule and trapezoidal rule, we start numbering at 0. So just keep that in mind. So x0 is a, which is 0. x1, right, is going to be x0 plus delta x. You're just adding delta x, so it's 1/2. And you can write these as decimals if you want. Unless it's thirds, like if it's halves or quarters, I'll use decimals. If it's thirds, I'll write them as thirds because, you know, you can't write like 0.33 is not 1/3. So you can't write it short with a decimal. but for half and a quarter you can. So you just add delta x every time. So x2 is going to be 1, right? We're adding a half. x3 is going to be 1.5, x4 is going to be 2, x5 is going to be 2.5, x6 is going to be 3, right? And I know I'm done for two reasons. Number one, n was 6, and number two, b is 3. So we got x0, x1, x2, x3, x4, x5, and x6. So I got my x's. Step 3. Calculate your y's. How much room do we have? So, right, remember how this goes. Y0 is f of x0. So f of, what's x0? 0, right? 0. But what is the function, right? You need the function. So the function is, what was it? 6x squared plus 3x. Right, the function you're integrating. So you plug in a 0, you're going to get 0. Y1 is going to be f of x1, which is 0.5. So I'm going to write this, but then I'm not going to keep writing these. So you have to calculate that. So grab a calculator or something. Y2 is going to be f of 1, which is 6, 1 squared plus 3 times 1. So that's going to be, looks like 9. Y3 is going to be f of 1.5. So 6 times 1.5 squared plus 3 times 1.5. Y4, f of 2, I'm just going to calculate them now instead of writing them all. 6 times 2 squared plus 3 times 2, 30. Y5 is f of 2.5. That's 45. And last one, I don't have room there, so I'll write it here. Y6 is f of 3. So we got 6 times 3 squared plus 3 times 3, 63. All right, so we have them, right? We have all of them now. So Y0, Y1, Y2, Y3, Y4, Y5, and Y6. So you have all your Y's. Once you have your Y's, then we can just calculate our approximation. So Simpson's rule with 6 is going to be delta x over 3, and then it's Y0, and then this is where you start alternating. It's going to be 4y1, 2y2, 4y3, 2y4, 4y5, and then y6. Right, so the middle ones alternate 2 and 4. But the first ones, or 4 and 2 actually, right? But the first one and the last ones are 1s. So what do we have? We have S6 is delta x was 1/2 over 3. And then you just put in your y values. So we got first one 0, 4 times 3, 2 times 9, 4 times 18, 2 times 30, 4 times 45, and then plus 63. So, you know, you got to, it takes a little bit of work. We've got 1/6 on the outside, and on the inside, you got to add all that stuff up. I guess if I am adding all that stuff up, I don't really need that much space. So you grab a calculator. 4 times 3 plus 2 times 9 plus 4 times 18 plus 2 times 30 plus 4 times 45 plus 63. You get 405. Just, I don't know why I put it over something. It's not, it's just 405. And then divide by 6 because it's multiplied by 1/6. I get 67.5. And that's my answer. So make sure you understand what this means. This means, so the integral from 0 to 3 of, why is it so big? 6x squared plus 3x dx is approximately 67.5. Okay. Now we weren't asked for the error, but you can type this into Wolfram Alpha if you want to know the exact answer. So 6x squared plus 3x. 6x squared plus 3x from, and it was 0 to 3. Actual answer, 67.5. Okay, so we're actually exactly right. And there's actually a reason why we're exactly right, by the way. So, let me just close that. I hope I don't have to write a lot of that again now. I hate it how it goes laggy when I switch tabs. Okay, what do we got? Okay, what was it? 405? That's fine. Okay, so 67.5, and so we said, so the integral from 0 to 3 of 6x squared plus 3x is approximately 67.5, and we checked it, and actually that's the exact value as well. Actually, we're exactly right. Now, why would we be exactly right? Why would it come up right? Well, think about it. Our curve was this. The curve is y equals 6x squared plus 3x. And Simpson's rule approximates your function as piecewise quadratic. Well, guess what? If you approximate a quadratic with a quadratic, you're going to get an exact, like, that's not an approximation. That's just what it is. Okay? So function as piecewise quadratic. So of course it's right. Of course, approximating a quadratic by a quadratic is perfect. Second degree with a second degree works fine. All right, but that's not theory. We need theory for this. How does this actually work? Okay, and so we need to look at the error formulas for these. You can actually tell how far off you are without knowing the exact answer. So error bounds. You can tell how far off, or how far off you could be, how bad or good your approximation might be without knowing the right answer. with the midpoint or the trapezoidal rule or Simpson's rule. They all have their own formulas. So how good or bad your approximation is without knowing the true answer. Now you have to be able to do this because otherwise this would not be useful in practice, right? Like if I say approximate an integral and you say, okay, I approximated the integral and I got 10. And I say, oh, you got 10. Well, how far off could that be? And you say, I have no idea. Then it's not good, right? You don't know, like, it's not a good approximation if you have no idea how good or bad it is. And so we need some kind of error bound to get us it. And we can't really prove this at this point, what these formulas are, but we can write them and we can use them, okay? So here they are. So these are the Airbound formulas. Each method has its own formula. Its own Airbound formula. They are as follows. So if we say like E with an S, that's going to be error for Simpson's rule. And if I say E T, that's error for trapezoidal rule. And if I say EM, I guess, error for midpoint rule. Okay, so they have a formula. They're not hard to use, but it's kind of a new thing for you guys. So here's the formulas. So one of them is this. So the error for the trapezoidal rule, I'm starting with that one because I can remember it. Don't say that out loud. I remember all of them all the time. So the error for trapezoidal rule is guaranteed to be less than m b minus a to the 3 over 12n squared. Now the m, what's the m, right? You know the b, you know the a, and you know the n. So when you look at these, you should go, okay, that's the b from the integral, that's the a from the integral, that's the n from the integral, and what is this? What's the m, right? And so the m is a number you have to calculate, and that's where the work is. So this is going to be where m is just a real number, positive real number, with this property. The second derivative of f, right, the function you're integrating, the second derivative of the function you're integrating has to be less than or equal to m. For, I should put the x in ab. Now just kind of, we're not dealing with that yet, just let it like sit in your brain. The error for the midpoint rule is almost the same. I believe it's 24n squared. Let me just double check that. 1 second. Come on. Yeah. Yeah. That's fine. Okay, good. So it's just a different constant down there in the denominator, which actually tells you something if you think about it, right? So if you look, you see that there's a 24 on the bottom there. So that's also where m blah, 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 f double prime of x less than m for x in AB. It's the same m. All right. So what that's telling you is that on average, the midpoint rule must have, like, the bound is tighter, right? Like there's a 24 in the denominator, so the error is twice as small because 24 is twice as big as 12. So the midpoint rule must actually be better than the trapezoidal rule a little bit, on average. Last one, and I'm going to make that vertical. So the error for Simpson's rule, it's the same exact kind of idea. I'm going to use a K, but not quite the same, because the numbers are all different. And this is where K is a number. I'm not going to write positive real number. That's obvious from the way this is set up. Not the second derivative. Fourth derivative has to be less than K for x in AB. All right? So those are your formulas. And every problem, like, they're all basically the same, and so the work is all the same. There's no like thinking harder about one of them or the other one. It all comes down to those derivatives over here, right? This is where, like, this is where your work is. This is where the work is. This is where the work is. Calculating those M or K. And a lot of times they use M for all three of them. I just used a different letter because it was a fourth derivative on the third one and the others were second. So it doesn't matter though. All right, let's try. So an interesting thing about this is you do not need to actually do Simpson's rule or trapezoidal rule or anything to actually answer these error-bound questions. You don't need to do anything. So what they'll do is they'll just give you an integral like this. I'll say example. I wrote example next to example. Nobody saw it. If I go like 0 to 4, and then I just put like 3x squared plus 2x here, and I say find an upper bound. That's how they usually say it, an upper bound for the error if we use, let's just say trapezoidal rule, it doesn't matter, with n equals, let's say 8. We're going to use n equals 8. We're not actually, so it doesn't matter. Find an upper bound for the error if we use trapezoidal rule with n equals 8 to approximate the integral. So what that does is it tells us how good n equals 8 is. So we know whether we could use n equals 8 or if we need to go with a bigger number or something. So find an upper bound. So here's what the steps are going to be for that. So first step is the formula, the error formula is, right, the error for trapezoidal rule is less than or equal to mb minus a cubed 12n squared, where m has to be greater than or equal to the second derivative. Now I know that I just wrote that in the other order, like I wrote the inequality the other way around, but it's fine, right? It doesn't matter what you write on what side. So this involves the second derivative. So it involves f double prime. So the first thing you're going to do is, like, actually I want to erase this. This is not step one. So step one is find f double prime, right? So you're going to start with f of x. That's what you're integrating. So f of x is 3x squared plus 2x. So you just take some derivatives. F prime, what's f prime? It's the derivative. So what's the derivative of 3x squared? 6x. What's the derivative of 2x? 2. All right. What's the second derivative? 6. Okay? Now, you need a bound, right? You need to choose m so it's bigger or equal to f double prime on a to b. Now, we don't actually care. Like for us, we can just say, well, f, that is actually 6, right? That's what it is. So why don't we just make that m? So use m equals 6. That's fine. That's easy, right? We just need a number bigger than the second derivative, bigger than or equal. So if the second derivative is 6, pick 6. Easy, right? Now then you just want to plug all the numbers into your air formula. So the air for trapezoidal rule is less than or equal to b minus a to the 3 over 12n squared, which is, and we just put them all in. So the m is 6, so you have 6. The b and the a are from the integral, right? So we got, dang it, there they are. B, A. So 4 and 0. So you just come down here and we go 4, 0, minus 0 cubed. And then you have 12n squared. What's the n? That was also given, right? We were also given that we have n equals 8. So you're just filling in the numbers. The only thing that you had to get yourself was the m. So you calculate this. So 6 times 4 cubed, right? So you just go 6 times 4 to the 3. That's 384 on top. 12 times 8 squared. That's 768. 384 over 768 is 2, I believe. I meant 1/2. 1/2, right? So when we say this, what we're saying is, so the error is at most 1/2, right? So that's an upper bound. So that's it, 1/2. 1/2 is the answer. And that's how you do that. Okay, now what you're gonna have to do though is maybe you see it coming that finding the m is the hard part, right? So that could be easy, that could be hard. So here's another example. So let's say find an upper bound for the error using n equals 6. I'm writing this awkwardly. Using n equals 6 midpoint rule. Or I should have said midpoint rule with n equals 6. On integral, I'm going to go 0 to 2. And my integral needs to be like a little bit bigger here. So let's say 1/4 x to the 5th minus 3 sine x. So I'm doing this on purpose here to show you something. All right, so we know what to do first, right? We're going to need f double prime. So we have f of x is 1/4 x to the 5th minus 3 sine x. So we have to take two derivatives. So f prime, take a derivative. You bring the 5 down in front, So you get 5/4 x to the 4th minus 3 cosine x. Okay, we need a second derivative. So you bring the 4 down in front, you get 20 over 4 x to the 3 minus, okay, oh actually the derivative of 3 cosine x is negative, derivative of 3 cosine x is negative 3 sine x. That'll turn the negative positive and we'll get 3 sine x like that. Okay? That's your second derivative. And that's a 5x to the 3 plus 3 sine x, right? It's fine. Next step, we need to find the upper bound. So we need to find an upper bound, or find the m, but find m, the upper bound for f double prime for x in AB. What's the AB for us in this problem? AB is 0 to 2. Right? That's the AB. Okay, so this is where the work is. This is where the work is. And it's not hard, but there's a couple tips that you need to know. So you write f double prime to start with, put it in absolute value, and say that is equal to the absolute value here. All right. So that is, why can't I draw a straight line? I don't care. So that's f double prime. Now here's a property you need. You need a property called the Triangle Inequality. It's very important in math, but you guys probably haven't even seen it before. You will if you keep going in math. So the absolute value of a plus b is always less than or equal to absolute value a plus absolute value b. That's what it is. So what that lets you do is say, well, this is going to be less than or equal. Actually, technically it's this is less than or equal to. And you just split it up into two separate absolute values. So you do the absolute value of 5x cubed plus the absolute value of 3 sine x. And that's the triangle inequality. All right. Then what you need to do is we just find a bound for each of these separately. So what you're going to do is just think about this one right here. Like for x values in 0 to 2, right? That's the a and the b, 0 and 2. Is it? Yeah, 0 and 2. How big can 5x cubed get? That's all you're asking yourself. It's not a hard question, right? Like in between 0 and 2, how big could 5x cubed get? Well, the biggest it's going to be is when you plug in the 2, right? Right? The answer is 5 times 2 cubed. 2 cubed is 8. 8 times 5 is 40. That's how big it could get. So, again, less than or equal. The biggest this could be is 40. So just put a 40 there. Now what about the 3 sine x? Well, for the 3 sine x, use the fact that you know for sine and cosine, right? The absolute value of sine x, how big could it be? The biggest a sine could ever be is 1, right? It could be -1, but we're in absolute value, so it's between 0 and 1. So the biggest it could be is 1. So you know that the absolute value of 3 sine x, well, the biggest that can be is 3. Because the sine x could be 1 and then times 3. So 3. So then overall, how big could this be? Just 43. So do you see how to do that? You break it apart and you just look at the parts separately, And you're able just to go like, oh, well, 5x cubed, the biggest that could be is 40, right? Because on 0 to 2, 5x cubed, this is as big as it gets. And then for the other one, 3 sine x, well, 3 sine x has to be less than or equal to 3. So there you go. So 40 plus 3. And you get 43. So then the question is, what do you pick for your m? No mystery. That's what you pick. 43 on this problem. Okay, so I know that that's a little bit like weird to be doing because it's not something that you're used to doing, but it is easy, pretty easy. So then step 3, we're just going to use the formula. So the formula was the airbound for midpoint rule. We're doing midpoint rule, right? What are we doing midpoint rule? Yeah. So the airbound for the midpoint rule was that the air is less than m b minus a to the 3 over 12, nope, it's 24. 24 in squared. And for us, let's just summarize what we know. The m we just found is 43. The b was 2, right? The a was 0 because we were going from 0 to 2. And the n was given to us as something, 6. So you just plug all those numbers in, and whatever you get is going to be your answer. So you just go 43, b minus a, 2 minus 0 to the 3, over 24 times n squared is 6 squared. So that is 344 on top. On bottom, 24 times 36, 864. So 344 over 864, 0.39. All right, so there you go. So the upper bound, for the air using midpoint rule, I'll say M6, is 0.398 for this problem. If you change the integral, you're going to get a different answer. Okay? All right. One Simpson's rule, and then we're done. All right, last problem. If you use Simpson's rule, with n equals 8, to estimate integral, we're going to go 0 to 1, e to the 2x plus cosine 3x dx. What is the max error? Or what is a upper bound for the error? Right? So same question, just with Simpson's rule, and there's nothing special about it. Like Simpson's rule is not any different than the trapezoidal rule or midpoint rule for this, except it's a fourth derivative instead of second derivative. So what do? We're going to need to find the fourth derivative. That's the difference. So what's f? E to the 2x cosine 3x. What's f prime? Got to take a derivative. So you're going to need a chain rule here. So 2e to the 2x plus, actually minus 3 sine 3x. F double prime. 4e to the 2x minus 9 cosine 3x. Triple prime. 8e to the 2x It's going to be plus 27 sine 3x. Fourth derivative. I don't know why I'm putting 4 primes. That's kind of a lot. 16e to the 2x plus 81 cosine. All right. So there you go. It, you know, kind of big numbers there. Then we need to find our m. Or k, actually, I guess. It doesn't matter. Call it m, call it k. It doesn't matter. Find k, the upper bound for the or the upper bound for the derivative. Roman numerals? Okay, sure. All right, so let's do that. So you're going to start with the fourth derivative. And then remember, there's an interval. What's the interval? 0 to 1. We might need that. So the fourth derivative is, in absolute value, 16e to the 2x plus 81 cosine 3x. You know that's less than or equal to, and then it comes here, less than or equal to, you can split this up. This is the triangle inequality again. You just do these separately. That doesn't mean you're finding like the best upper bound or the closest bound, but it's a bound, and a bound is all we need. All right, so we have that. So how do you do this? Well, just keep in mind what these functions look like, right? Like an exponential, what's an exponential do? Goes up, right? That's what like y equals 16e to the 2x does. And so if you've got 0 here, and you've got 1, and you've got 1 here, where is it biggest, right? It's going to be biggest on the right. So this is going to be biggest at x equals 1. So this is going to be less than or equal to, you put a 1 in here, which will be 16e to the 2 times 1 plus, all right, 81 cosine 3x. How big could that be? Just 81. Remember what we said, right? Cosine has to be, cosine in absolute value has to be in between 1 and 0. So the biggest it could be is 1, and then times the 81. So what do we get? We get 16e squared plus 81. That's what we get. So what are we going to choose for m? That, right? It doesn't have to be like an integer or something. It could be a weird number. So this one's a weird number. Oh, we said we were going to call this k, right? Didn't we? All right, k. So we called it k. So again, that wasn't hard, but you have to think a little bit about like how big could 16e to the 2x be in between 0 and 1. And this is, that's this piece of the curve. So it's biggest at 1. All right, now last step. What color were we using? Purple. So step 3, use the formula. So the formula was the error bound for Simpson's rule is less than or equal to, or the error of Simpson's rule, and it was k, because we called it k for some reason, b minus a to the 5th over 180 into the 4th. Is that right? Yeah, that's right. So what are our numbers? The a is 0, the b is 1, right? Because we're going 0 to 1. What was the n? They gave it to us. 8. 8 subdivisions. And then we came up with the k, and the k was annoying, but there, 16 e squared plus 81. So you just fill in the numbers. So 16e squared plus 81, parentheses, 1 minus 0 to the 5th. Hey, that's easy at least. That's 1. 180 into the 4th, that's 8 to the 4th. 8 to the 4th is a big number. All right, so work out the top. Oh, I don't know where E is on this calculator. It's a new calculator. E. If I were in E, where would I be? I'd be next to the pi, but I'm not. Oh, no? Oh, I almost said a square again. Hold on, let me try this. That's the wrong thing. Found it. Ha ha ha, you tried to hide, but I found you. 16 e to the 2 plus 81. It's about 200. Divide by, I guess I'm just going to do this all in the calculator. Divide by 180. Divide by 8 to the 4. I get 0.0002702 dot dot dot. So that's very small error, right? Back there with n equals 8 here is very small. But that's my answer, right? That's the upper bound for the error. All right. So that is done. We'll go back here. Scroll here. All right. So that's done. We did several error bound problems. There is more stuff you can do with the error bound. I just feel like I don't think I assigned it. So we're probably just not going to do it, which is fine. This is good enough. All right, so that's it for this lecture. That was an hour and a half plus the other half hour, so another like 2-hour lecture for you guys. Lots of fun. All right, see you next time.